All right, with that said, so the goal of this session here, the community modeling in dynamic material flow analysis session, is that Stefan and I had the thought that scenario models for future materials or material futures and dynamic stock and flow models are models which have very often high resolution, they are data intensive, and they're computationally challenging. There has been efforts to make this more accessible and also more computationally viable, so to speak. For example, with the Open Dynamic Material System model, which was developed 1.5 years, developed and published 1.5 years ago in the Journal of Industrial Ecology. The authors of that paper, Stefan Palyuk and Nico Hiran, are also here. That was developed to facilitate data handling and to increase the transparency, reproducibility, and comparability of dynamic material flow analysis models. It was programmed in Python. The first models which are programmed in Odm are now available. The related databases are partially or fully published. However, there is a significant entry barrier to do that. In parts because there's a lack of a graphical interface. There is still only a low number of case studies. So to speak, we need more positive examples to spread the word, so to speak. And in this session, we would like to go into dynamic material flow analysis, show positive examples, talk about the comprehensibility, the reproducibility, the comparability of specific models, and what we as a society and as a scientific community can do to foster that. So as said, we will have these 4 presentations now first, and afterwards a general panel discussion where everyone can join in. And of course, you can also ask questions in the chat or then verbally later on. So in that, with that said, I would like to stop my presentation here briefly and give the word to Esther van der Voort. Esther van der Voort is an associate professor at Leiden University at the Department of Industrial Ecology at the Institute of Environmental Sciences, CML, in Leiden in the Netherlands. She specializes in methodology development, life cycle assessment, material flow analysis, substance flow analysis, natural resource accounting, and indicator development. In particular for the bio-based economy, for metals, and the circular economy. She's also a member of the United Nations Environmental Programme International Resource Panel and in the ISIE Vice Treasurer. The topic of her speak will be dynamic MFA in scenario assessment, supporting resource policies and strategies. With that said, Esther, the floor is yours. And
thanks very much, Christoph. Then I should share my screen again. Yeah, here it is. Do you see it?
Yes.
And then we are going to do it full screen so that you see it even better. Thanks for your nice introduction, Christoph. My presentation won't be so much about all the data-oriented stuff that you mentioned. It will provide some examples that I think are nice examples, and I will conclude with some remarks on where I think we should go with these type of models in general to be relevant to support all kinds of resource-oriented policies. This is for the resource-oriented policies, the starting point. These 2 pictures come from the global resource outlook of the International Resource Panel, where at global level, the resource challenge is really put down. It boils down to this. The resource extraction has increased by a factor of 3 over the last 50 years, and it's expected to grow by another factor 2 over the next decades until the mid of the 21st century. So that is quite a powerful development. And the big question is how to make that sustainable while still enabling development. This is sort of the tension between the different sustainable development goals. On the one hand, we want development and we want developing countries to build up their infrastructure. This requires a lot of materials. And on the other hand, we would like to reduce all kinds of environmental impacts, land use, climate change, etc. How to do that? Well, you can use scenarios as a tool to sort of look at different directions for development and how they would work out. So scenario analysis you can see as a tool for decision making. In climate science and policy support, it has been used for a very long time. And now we see, among others, in the International Resource Panel, a first attempt at developing also resource scenarios. And I think that dynamic material flow analysis, among others, the ODIM model that we are talking about here today, is really an essential tool in such a scenario context. Just a few words, not too many, because probably you know all this, but I think it's always important to emphasize those stocks in society that are at the core of the dynamic MFA models. Why are they so important? Well, in the first place, it's the stocks that represent the value and that represent the functionality, not so much the flows. The flows are more, what needs to flow into the stock in order to keep it up to size or up to function. Stocks are things that saturate, and that is very important if you think about sustainable development and about the circular economy. The fact that stocks can saturate is really very important for that. Stocks are urban mines. They are the sources of the secondary materials that we can access in a circular economy. And it's the stocks that determine the flows, both the inflows, the demand, and the outflows of the waste. If you look at dynamic material flow analysis, where stocks are the core, you see that it takes effort to translate the available information into the stocks and flows, and that often in the models like ODIM, a bottom-up approach is taken. First, we start from the service or the function, then that is translated into a stock of certain products. Like here in this example, you see on the left, the cars. We have data on person kilometers, and that needs to be translated into the car fleet, the stock of cars that are actually there. Then the next step is to translate that in material terms, so how much materials are embedded in that stock of cars. And then finally, that is again translated by the help of things like lifespans in terms of waste, flows, and sales, car sales, so the demand and the waste. Now for the examples, we too at CML have used ODIM, and we have done that in two projects. The first one is rather a series of projects supporting the Dutch circular economy policy. Our job in that series of projects is to investigate the Dutch urban mine and its potential to reduce primary input. So step one is collecting data on the present urban mine, so prospecting really, how much is there, where is it, and what exactly is in it. Step two is then to specify what comes out of it in the future. And then step three, we haven't got there yet, that is something for coming years, is to specify what can we do with that outflow, how can we reuse it, repurpose it, recycle it, etc., put it back into our economic system in some way or other. For this first step, it's really a data collection thing. So we used GIS a lot for the bigger stocks in buildings and in infrastructure. GIS is a very useful database. Also, we used the national statistics as are collected by our Central Bureau of Statistics. Step two what comes out of it in the future, there the dynamic MFA comes in. And for that step, we used Odm. Step 3, is a very broad thing that involves technology. It also involves business models. It involves policy. So that is something that has still to come. These are some results from that exercise. The inventory of stocks in buildings. You can represent it geographically, like in the map on the right hand. You can see then there where the largest concentration of the materials is. This is just in tons altogether, but you can also make maps like that for specific materials, like steel or concrete or whatever. And on the left-hand side, you see it broken down into the different types of buildings, 4 types of residential buildings and 7 types of utility buildings. This looks very simple, but it was quite a job, as most of you will appreciate. This is another picture to show that also we use students for this type of research. They find it very interesting to actually contribute to a real life project. Bas Roelofs, he investigated wind power, so a past time series of the capacity in megawatts of installed power in windmills, onshore and offshore. And then on the right-hand side, using Odm, results for the future. This is one of the 3 scenarios that he actually looked at, and those results are for steel. This is another student, Judith van der Horst Verschelling. She investigated the electricity grid, so all the cables that are underground and also a few above ground. And one of the conclusions that she came to, also using dynamic material flow analysis, was that there is now already a huge stock of hibernating materials in the soils of cables that are no longer used, but are just left in the ground. And this hibernating stock is expected to grow significantly, especially for aluminium, because, well, in new cables, hardly any copper is used anymore. It's almost all aluminium nowadays. So this hibernating stock is really expected to grow a lot. And this is just material that lies around doing nothing. Of course, it's a bit of a hassle to take it out. That doesn't make it easier that it's in the built environment where you have to dig in the ground. But you can think of ways to actually lay your hands on those materials. Second case I would like to talk about is the global level project that we do to support the International Resource Panel's Global Resource Outlook. The GROW 2023 is actually coming up, and the plan is to include scenarios for resource use here as well, starting from the SSP scenarios that are also used for climate change, and then defining resource variance with it. That means that resources or materials modules have to be developed to add to integrated assessment models. Sebastian Deetman, I guess most of you know him. He has been working on that for the past years already, also using Odm as a starting point. Odm has been used also in the IRP report Resource Efficiency and Climate Change that some other people of this audience have worked on. This is a result of Sebastian's work, the global copper stock in 3 important applications in buildings and vehicles and in electricity infrastructure, and how it develops over time. In the middle, you see the copper demand, and on the right, the outflows. And you see here that the outflows, they are growing, but the inflows are growing likewise. So they're as yet, and also in 2050, nowhere near the level of the inflow, which means that for this applications, cycles cannot be closed yet. The results are available for, I believe, 27 world regions or 26, something like this. But here you see it aggregated to 3 different world regions: the developed countries as a group, the developing countries, and then China and Japan as a separate group, based on the development of the stocks and flows in their countries. In China and Japan, you see that actually the inflow starts to stabilize towards the middle of the century. And in the case of aluminium, the top one, the outflow, which is the dotted yellow line, actually approaches the inflow. So there is an opportunity for closing cycles that will present itself near the middle of this century. Then some last words, first on data. In this work, we come up against a lot of missing data. You see that statistics at all scale levels focuses on flows and not on stocks. And that means that there's only in incidental cases, there's good data on the stocks. For the car fleet, we have data, but for many, many, many other applications, we don't. But there is flow data. A second thing is that if you want to say something about materials, you will have to know the composition of the products if you use a bottom-up approach like this. So you need material composition data, also changes in that data over time, and the same for lifespans, lifespan distributions. Also that changes over time, and you need that information, and it's often not available. From the supply side, you see that GIS data can be very useful. So it says here, especially for infrastructure, but it's also especially at the lower scale levels. The lower the scale level, the more useful these GIS data are. Problem is that they often have no memory. The thing in GIS is to update it to as near the present as possible, but then the past systems are often lost. And there's all kinds of other information that could be used, and to some extent we did use it, but that are only incidentally available. And if we really take this seriously, it should become much more standard. Finally, some on direction of development of dynamic material flow, in my opinion. It's an essential tool to support resource policies, also energy policies. And what it basically reality, and it models the interface between society and the economy on the one hand, and the environment on the other hand. And this physical interface has its own dynamics, and is therefore very important to include in the sequence of models that is used in integrated assessment. Now, dynamic MFA already has proven itself in a number of case studies. The body of literature about that is growing. I think that the main challenge for the future is that we have to develop it from stand-alone models into a standard addition to other models. So it needs to be able to connect, on the one hand, to models of the society and the economy, and on the other hand, to models of the environment. Otherwise, it cannot be a real interface between the two. And if that happens, it can become an essential element in scenario assessment at all scale levels. That was it. Thanks very much for your attention.
Thank you very much, Esther, for the very nice presentation. Round of applause from the audience as well. We do have time for maybe 1 or 2 questions. Would anyone like to be the icebreaker? In that case, let me ask you one question, because you already said that some of your slides that you showed were from students' work. So how accessible is Odm for students?
Well, that's a very good question, actually. We used it in the latest version of the material flow analysis course that we taught in our industrial ecology program for about 60 students. And we find that in the end, Well, I think 90% have been able to use it. The other 10% has fallen back to alternatives like Excel. But actually, with a bit of guidance, it's very well possible to use Odm in this framework. And we are actually very happy that it exists and that it's there to be used for us.
Stefan, I think you're still muted. But
I just want to say that's really great to hear. Is thank you so much for the input you gave, and also for that it's actually working. I mean, this is exactly why this software was designed, right? And then in the panel we can see later how we could move this forward. But thanks already now.
yeah, is there one more question directly to Esther now? And otherwise, I would leave it for the panel discussion later on. Okay, doesn't seem to be the case. In that case, we will move to the second speaker. Thank you once again, Esther. And the second speaker will be Zizao from the University of Antwerp in Belgium. He's a tenured assistant professor at the Road Engineering Research Section, Energy and Materials and Infrastructure and Buildings, EMIB, at the university. He has been a postdoctoral fellow both at the Northwestern University in the US as well as the University of Southern Denmark in Denmark. His talk is going to be about Imagine Concrete, integrated modeling of the material energy emission uptake nexus in the cement and concrete cycle. Z, the floor is yours.
All right, I'm gonna close the camera in case of the poor connection, so to save the bandwidth. All right, and good evening, good morning, everyone, and thank you so much for inviting me to join the discussion. My name is Zhi. I'm now assistant professor at the University of Antwerp. I'm now building a small group themed around sustainable infrastructure and built environments. And prior to joining University of Antwerp, I was a postdoc at Northwestern University and University of Southern Denmark, working with Professor Eric Massenet and Professor Garnier. And today I'm going to talk about how to decarbonize the cement and concrete cycle from a whole life cycle perspective, and combining dynamic material flow analysis and life cycle assessments. Although our modeling framework is not based on Odm, the main logic behind it is very much in line with Odm. And hoping that my research can shed some light on how integrating MFA with other tools could help us, explore decarbonization pathways for the cement and concrete sector, find synergies among the community, and eventually open up new research opportunities. And this work is made possible by an outstanding group and the philanthropic funding from Tamarix Foundation. And so why cement and concrete matter? A quick answer is because cement and concrete are key ingredients to our modern civilization. Therefore, the massive production of cement and concrete has contributed significantly to global CO2 emissions. And in 2014, cement production alone has contributed about 7% to the global direct energy-related CO2 emissions. And cement production efficiency has progressed over the past decades, mainly coming from thermal efficiency improvements and fuel switching. Our recent climate ambitions have called for achieving net zero emissions by mid-century, which requires radical technology interventions. However, population growth and associated built environment needs will make cement and concrete decarbonization more challenging, as indicated in the graph here. So what decarbonization levers we could leverage to help us tackle this challenging transition? And in this work, 7 major decarbonization levers are considered. The first lever targets at the cement plant. It involves retrofitting the cement kiln, improving the management and operations, and incorporating more low carbon fuels such as biomass. And the second lever refers to adopting new cement formulas to reduce the process emission and thermal energy requirements. And the third refers to replacing ordinary Portland cement clinker with supplementary cementitious materials, which have similar property to the former. And the next one refers to utilizing at plant CCA's technologies, which target at fuel combustion processes and end of pipe of the cement kiln. And the next one refers to incorporating CO2 into concrete manufacturing or using industrial alkaline materials to mineralize CO2. And the resulting products can be used as aggregates for concrete. And the next lever includes 5 major material efficiency strategies. And the first 3 strategies can directly reduce cement use per square meter in terms of buildings or per kilometer in terms of roads. And the last 2 strategies can reduce the needs for new construction. And the last lever refers to end of life options. And this lever includes measures that can reduce the demand for raw materials or measures that can accelerate CO2 uptake. And to bring together all these levers, we developed an integrated analytical approach to exploring technological opportunities in the cement and concrete cycle. And we limit our scope to 3 major cement producing or concrete producing and consuming countries or economies, the United States, China, and India. So we can ensure that the conclusions arrived from these analyses are generalizable to other countries or regions. We also distinguish between the levers on the production side and the levers on the demand side. And these levers are usually examined in isolation, but many of these levers are interrelated. So the overarching objective of this work is to use material flow analysis and lifecycle assessment to capture those interactions and then explore possible pathways for deep decarbonization. So essentially, we will have 2 deep decarbonization pathways, a production-centric one and a whole systems one. And besides these 2 deep decarbonization scenarios, we also construct 2 scenarios as references, frozen progress and current ambitions. The first one assumes production CO2 intensities for cement and concrete will remain unchanged, which is kind of counterfactual. And the second one reflects the current ambitions of industries and policymakers, and the technology progress is moderate. And due to the longevity of buildings and roads, cement and concrete will stay for decades in building stocks and road stocks. And a number of our levers have far-reaching impacts over time. So we developed a stock flow model to physically keep track of the temporal dynamics of material demand and end-of-life material availability. And this allows us to capture all the nuances entailed by those decarbonization levers. On top of that, our stock flow model is able to distinguish different types of buildings and roads. So we are also able to project newly constructed for area and road length by sector, therefore cement and concrete demand by sector. And for better presentation, I aggregate the result into fewer categories. And I would like to point out that the magnitude and trends of cement demand or cement and concrete demand is the joint effect of each country's population size, per capita floor area, lifetime of buildings and roads, architectural and road design conditions, as well as historical development of building stocks and road stocks. So obviously, the trajectory of cement and concrete demand will shape the overall trend of CO2 emissions, which will be observed from the scenario results in later slides. And in addition to these granularity, our model also allows us to look into both CO2 released and stored over the life cycle of concretes. Here, I would like to highlight several key CO2 fluxes. The first CO2 flux is related to biogenic fuels and CCAs, which is called BECCS. And the second CO2 flux is related to carbon utilization, which enables or enhances CO2 absorption in cement-based products or industrial wastes that contain alkaline minerals. And the third CO2 flux is the natural weathering of cement-based products. And as you know, over the lifespan of cement-based products, CO2 will slowly react with calcium silicates in a cement and be stored in cement permanently. And this phenomenon is called cement or concrete carbonation. And the last CO2 flux represents an alternative route of using biomass to remove CO2, and that is replacing concrete by mass timber. And adoption of mass timber in buildings will enlarge the carbon pool in buildings. And having this level of granularity in our model allows us to distinguish CO2 emissions and CO2 uptake from different sources. And then we will use the balance of positive and negative CO2 fluxes to present our scenario results. And in order to present the contribution of each decarbonization lever, we employed a wedge approach to visualizing our scenario results. And in the following slides, we will use the results of frozen scenario as a benchmark. And in addition, we use bar charts to visualize the cumulative contribution of each wedge from 2018 to 2060. So we will have a better sense of the contribution of each lever. As you can see in the production-centric scenario, those decarbonization levers which were utilized in the current ambitions scenario will be turned up to a more aggressive level, plus additional contribution from lower carbon cement chemistry and CO2 utilization. So lever 2 and lever 5. And so what we can read from the graph here is we will be able to achieve net zero through a production-centric decarbonization pathway. And most likely the cement industry or the cement and concrete industry has to rely heavily on CCAs. Now, if we opt to take a whole system route where CCAs and lower carbon cement chemistries are less relied on, instead cement demand or concrete demand reducing strategies are more relied on. We will also be able to reach net zero by 2060. Essentially, these demand side levers could give us a wide range of mitigation space and allows us to release our pressing demand for deploying CCAs in the production site. And the cross-country comparison shows that lifetime extension will start to play a pronounced role in China and India after 2040. And for the United States, the effect of lifetime extension is rather small because the lifespan of United States buildings is longer, which makes lifetime extension much less effective. And here comes a few key findings from our study. The first finding is accurate modeling of cement and demand and mitigation levers requires consideration of multiple factors, including population, living standards, building codes and regulation, construction practices, material selection, lifetime structure, and historical stock development. And the second conclusion is deep decarbonization of the global cement and concrete cycle is possible with existing technologies and those currently in the innovation pipeline. And a production-centric focus requires heavy reliance on key technology improvements, low energy or low carbon cement chemistries, clinker substitution, and CCAs. And the whole systems approach reduces pressure on production side solutions through material efficiency strategies and, of course, broader stakeholder involvement, such as architects, urban planners, etc. And we have also converted our Imagine concrete model into a web-based version, which allows users to define their own scenarios and change the value of the decarbonization levers considered, so we can engage more, with the stakeholders involved. And yeah, and thank you for listening. If you have any questions, please feel free to ask. I'm also looking forward to the panel discussion later on. Thanks.
Thank you very much, Zhe. Round of applause also once again from the whole audience. Thanks a lot for this very interesting presentation. Once again, questions from the floor directly to this talk. Peter.
Hi, I have a quick question. Thanks, Zhe, for the nice presentation. I'm curious, what is the extent for reducing the carbon intensity of cement production? I saw one of the main levers or strategies in this regard was the low carbon cement chemistry. So my understanding was I didn't think that there was much potential for reducing the carbon intensity of cement production, but so I'm curious how much potential there and how that can be achieved.
First of all, I would like to clarify so what lower carbon cement chemistries is. So basically the most widely used cement is Portland cement, ordinary Portland cement. And actually there are a wide range of cement chemistries or cement formulas that have lower energy requirements and CO2 emissions. And of course, these cement chemistries are not are still in the pipeline, and the performance of these cement chemistries still requires further investigation, because you have like durability concern, you have safety concern, and so on. So you have to do a lot of experiments to validate the performance of these cements. But we do see potential, from these lower carbon cement chemistries, and we based our assumption on some experiments, and also we considered supply limits of these lower carbon cement chemistry, because some of them require specific materials, for the cement, for the clinker making.
Like slag, like GGBS, is that kind of one of the alternatives you consider, or is it something else?
I think are you referring to geopolymer? If so, so we are not considering geopolymer. We regard geopolymer as in level 3, which is basically reducing the clinker to cement ratio. And for lower carbon cement chemistries, here we are talking about changing the row feed for clinker making. So basically we change the formula of clinker.
Okay.
Not concrete. So you start from clinker to cement and then to concrete.
Okay, thank you.
Yeah.
Yeah, I think we can have one more question from Stein. And if you can, asking for a quick question and quick answer, maybe possible, if that's possible.
Okay, thanks. I'll try to make it very short. I'm just wondering about the use of waste in the industry, either as a substitute for clinker or as a substitute for fuel, as an alternative fuel. Did you run into any trouble in terms of emissions accounting, and what do you sort of recommend? Like, how should we look at that in terms of actual avoidance of emissions?
So what we did is we assumed that these. So basically, I think you're talking about biomass used, to replace conventional fossil fuels, right? If that's the case, so here we made assumption that these biomass is carbon neutral, and this is one of those our assumptions. Yeah. And
what about fossil waste, like tires and so on?
Oh yeah, we do consider CO2 emissions coming from this municipal waste. Yeah. Of course, the CO2 emission coefficient is lower than coal, than coal or maybe some other fossil fuels. But indeed, these recycled or recovered municipal waste do have CO2 emissions, and we consider them as positive.
Thank you very much, Zee, once again.
Thank you. I'm going to stop sharing my screen.
With that said, we will move to our next speaker, or in this case, speakers. Dominic or Jan, whoever wants, can share the screen now. Dominic, okay, very well.
Yes.
So the next speakers are going to be Dominic Vidanova and Jan Strick from Co2 Vienna. Both Dominic is a senior scientist at the Institute of Social Ecology at the University of Natural Resources and Life Sciences, Co2, in Vienna. And Jan Strick is a PhD candidate at the same institute. Their topic will be on modeling global economy-wide material flows and stocks at national resolution for 16 materials and 150 years, the Odm MISO 2.0 model and its next steps.
Okay, thank you very much for having us here. Thanks for the nice introduction. I'm sharing this presentation because Jan is actually doing a lot of the work on Odm, so I think he's more qualified to actually say something on it. Well, yes, I already started this part. So what are we doing? So we are very interested in kind of a comprehensive economy-wide perspective, and we are doing this because we're working as part of a large ERC advanced grant project, which looks at understanding the role of material stock patterns for the transformation to a sustainable society. And as a kind of guiding heuristic, we use this idea of a stock flow service nexus, which can be used to develop interdisciplinary research on different kinds of provisioning systems which deliver services to society at hopefully maybe lower resource use and less emissions. And in that sense, we are very much interested to always look at stock flow combinations and their social outcomes, so to say. And one of the research streams in this rather large project further develops our work on inflow-driven top-down MFA modeling. So we start out from kind of a comprehensive metabolic systems perspective, looking at fossil fuels, metals, ores, non-metallic minerals, and biomass flows. We all know that there is kind of internationally standardized methods and global databases, which give us at least some information on extraction and trade of these materials. And we want to kind of extend on this work. So this is what I actually did as part of my PhD. This is kind of the standard economy-wide MFA perspective, where you have some standardized and harmonized indicators looking at basically inputs and outputs to the socioeconomic metabolism. And in my previous work, we kind of opened up this black box and turned it into kind of a little bit more of a colorful space with lots of boxes where we discerned energy uses, material uses, where we integrated a dynamic MFA model in blue here. And this was actually done many years ago in MATLAB, and it had a lot of the features that Odm also had, but it was only me fighting against coding MATLAB. So I'm very happy that actually Odm has been developed so we can connect to this, because we have some nice features here, and we used a lot of that in some publications that some of you might have seen. So we have looked at global socioeconomic stocks. We have looked at the entire metabolism using this kind of data. We also looked at the global circular economy over the last 120 years. But we were always a little bit unsatisfied because we were not really discerning end users. We were not really discerning different countries or going to finer resolutions. Also, data quality is obviously always a big issue if you start out with international data sets. So in this large Mudstocks project, we actually have the opportunity to spend quite some time on these issues. So we actually have 3 steps to address our aims. So we want to develop comprehensive long-term estimates of the major material cycles, differentiate end users, and model the dynamics of material stocks. And for this purpose, we start out with developing a comprehensive data set on 14 material cycles or material flows, long time spans, historical data sets. We compiled a lot of information to get this data straight. We actually have kind of a 10-step procedure, which we consistently applied across all the materials to really get a robust and harmonized data set out of this, which can also be kind of clearly communicated how we achieved this data. In the second step, Jan, this is where Jan is going to take over. We look at we take a little bit of a critical look at different methods to look at end-use splits in dynamic modeling, and then we connect to the Odm framework. So let us just jump into this. So you might still remember the gray colorful boxes that I showed before. This is the latest iteration where we are moving closer and closer to principles of material flow analysis while being consistent with system boundaries developed for economy-wide MFA and metabolism research. We actually have in the scope on the center left, you can see the scope of this work. So we include lots of materials and countries. We do systematic uncertainty assessment, also to the data and to the interpolation and extrapolation methods that we had to use to get to this data. And just as a kind of a teaser, we are currently working on the paper here. So the uncertainty ranges that you can see, they are actually derived from a kind of systematic procedure and an openly kind of visible procedure, which people can also change if they think uncertainties should be different. So I'm very happy that we achieved that. We can also see that we look at data quality in terms of how much data did we have to estimate, how much mass did we have to estimate, how does it work along the processing stages. So this is some of the ongoing work here. And this gives us a good starting point for our modeling, because if we know for the last 200 years, basically, how much primary materials were used and processed and manufactured, we can then model stocks from them. And now I'm handing over to Jan.
Yes. Hi, thank you, Dominic. So what Dominic just presented in step 1 is basically the assembly of material use on a very aggregate level for our inflow-driven model. And as Esther and others have pointed out, actually, what we want to do is connect the material use to services. And for this, we need kind of to know in which products these materials are used, and how it is also sometimes called or different end uses. And in order to kind of see which methods are out there, we conducted a little literature review. And we found that so far in many inflow-driven MFA studies, so-called industry shipment data has been used, which is data in physical units, which says basically which crude materials go to which manufacturing sectors, for instance, construction or transportation. And with these, you can then split these primary or secondary material use to these different end uses, which are rather on a sectoral level than on a product level, actually. And while this has worked well for some data-rich countries, on the global level, it's actually a big problem, as lots of this data is fee-based and very scarce. So that recent studies also looked into other kind of data, for instance, monetary input-output tables, as these are more readily available and also potentially offer quite a high resolution in terms of products or sectors. And there are a few papers out there which all use a certain type of analytical approach to that. And we are currently applying these different methods to the USA as a data-rich case studies to see how they compare, with the goal to then use these methods together with Exiobase for our global MISO2 database, basically. Yeah, we can expect that most probably these end users will rather be on a sectoral than on a product level. So we'll have to see how we can get to more detail here. So these two steps now, step 1 and step 2, basically provide the input data for the Odm MISO2 model, which I will come to now. For which we also kind of extended the system definition that you saw at the beginning, which is rather on the conceptual level of economy-wide material flow accounting, towards a more technical description that is more common in material flow analysis. And for our Odm MISO2 model, which you can see here, each process and flow is labeled, and which can then also be the solution of the system is more transparent. And what you can see here is our current form of the system boundaries for our Odm MISO2 model, for which we can then basically trace the extraction of these 14 materials through different processing steps, the stock use phase, and also end of life management. Yeah, and as Dominic already said, to put this system definition into code, we use the Odm modeling framework. And of course, we use the kind of the modeling backbone, the classes and functions, and the inflow-driven part of the dynamic stock model. And in addition to that, we also want to code some maybe MISO2 specific submodules, like for instance, the estimation of sand and gravel that is required for road base courses and building foundations, and also how much of this is estimated to come from virgin or recycled materials. as has been partly implemented already by Dominic in the first version, but now has to be transferred to Python code. And as a second module, also this semi-quantitative uncertainty assessment needs to be implemented as a sub-module and then fed to the Monte Carlo simulations. And yeah, we are kind of still in the developing phase, so we don't really have any big results to present yet. Yeah, we are working on implementing the Monte Carlo simulation soon, hopefully. And at this point, we also want to thank the developers and contributors of Odm and for Odm, yeah, to provide such a modeling framework, and also Christoph Helbig, who shared some code of his work for implementing Monte Carlo simulations in the Odm framework, which we will use and try to apply for these many materials, and hopefully also optimize a bit in terms of runtime, as we otherwise might face a little bottleneck there. So this is it regarding kind of the basic MFA framework that we are developing. And on top of that, we also plan some more modules, like for instance, an energy use and greenhouse gas emission module to also be able to model the resource climate nexus. And yeah, we hope to code these modules in a good way so that we can also play them back to the Odm and general dynamic MFA community, and then hopefully also provide them open access, open data, open code, or at least intermediate results and the methods. And with this, yeah, we are concluding, and thank you very much for listening and looking forward to the discussion. Thanks.
Thank you very much, Dominic and Jan, for your very nice presentation. Round of applause once again. So the floor is open for any questions directly to this presentation. Yes, Peter, again, I would say.
A very quick one. Again, thanks for the presentation. I just wondered, in the end, you talked about the dynamic modeling of the foundations and substructures. Can you describe what you mean by that?
Yeah, that's a very good question, and that's actually a bit of a tricky part. So as we all know, sand and gravel is not very well reported. Let's put it like this. But we know these are huge material flows, and there are substantial impacts to these, especially if you look at other ecological issues than climate change. So for us, having these kinds of materials covered is really important. And we do know from kind of bottom-up stock-driven modeling that, for example, road stocks have substantial amounts of sub-base courses, as they are called. Also, buildings usually have some kind of, in the UK, they call it hardcore layer, or kind of foundation layer underneath the concrete structures. And these materials can amount to a lot, basically, but it's very, very hard to really capture them well. So what we do is basically we take stock-driven modeling that we do in other contexts, and we basically derive a kind of relation between how much bitumen do you need to build a road and how much sub-base courses are there to the roads based on the bitumen amounts. And these change over time, these factors, and they also change basically in terms of how much stock there is already. So if you have a large stock, you basically maintain only parts of it. So you need less sand and gravel for new sub-base courses, for example. So we try to approximate these kinds of dynamics building on previous work. This is something we have already done in all the papers that I've shown. And here we are now trying to kind of make it more robust with every step. Trying to bring in world, regional, or even country level data to differentiate this even further. So it's a bit of a tricky issue, but in the end, it's a kind of multiplier which moves with concrete and asphalt amounts and bricks.
Sounds great. Thank you very much.
Do we have more
Could
questions?
I ask something? Yes, yes.
Go ahead.
I don't see where I can raise my hand. I seem to have
I think
lost
as a
it.
co-host, you can't.
Oh, right. There.
Go ahead.
But I do have a question. It's very interesting. You start really from the other way that we did. We started very much bottom up, and you started top down, and we are meeting somewhere in the middle. This is quite interesting. have you compared your results from publications that have done a more bottom-up approach to see whether they at all match the stock data, so to say? That would be very interesting to see. Yeah, do we indeed come together, or are there big discrepancies that we have somehow still to deal with?
This is a very, very good question. Thank you very much for pointing that out. So validation is really important to us. So in the supplementary information to all the papers, we usually try to compare our estimates against a lot of the literature, let's put it like this. The thing is that we need at least the same, let's say, system boundary. So a kind of local or regional estimates are very hard to compare against national to global estimates. But if we find studies which do national level, we try to put this into the comparison. So a lot of the, especially in the PNAS paper, I spent lots of time compiling country level estimates and also the more material specific estimates from Stefan and Z and others who did global modeling or country level modeling, and validated that against our results. And we actually find relatively good agreement. But I also have to say that in the end, most of the studies circle back to the same data sources. So in that sense, they're not really that independent. And I have seen very little real independent data that we can really compare against, as we have this constraint that we need at least the national scale with at least a similar system boundary. So
yeah, there's only a few studies that have done that actually.
Yes.
For example, use GIS as a database, because that is really coming from a different corner of society.
Yes. Yeah, so sorry, the few studies we are in the same ballpark, I would say. If you so I mean, we're all circling around something like 300 to 400 tons per capita if you look at the high income countries and a large coverage of materials, but this is still a big range. So this is not close enough to an actually robust agreement.
Thanks.
Thanks. Stefan, you have raised your hand.
Yes, this is a wonderful observation, also wonderful presentation, Dominic and Jan, thank you. You know, Rick Lupton, who also chaired the Uncertainty MFA session, said we need to become better at traceability. Exactly as you said, Dominic, right? We trace back to the, we need to, I mean, we can consolidate knowledge, right? We say, hey, we have this data set, Comtrade, material composition, and then we have one best estimate. Maybe what you produce is now close to it of the material stocks. Or we have a completely independent satellite image or whatever. And we need to somehow clearly flag, hey, this is or this is the same data source, but different estimations. This is different data sources and so on. And here we can reconcile. So there will be also more work in the future. And then I had one quick question. These 200 years, how far in the future do they go, or what are your plans for scenario modeling?
That's a good question. Yeah, the years always change depending on how you count it. So our modeling, it starts from kind of an idea that at some point, obviously, you have to start with zero stocks because we can never know stocks in 1800. So we use what we call a spin-up period, and we usually start basically in 1800, very close to your steel data, for example. And this is a kind of a time period which we usually do not show in the results because we think this is really just a rough ballpark to get the stock flow dynamic going. So depending on if you start counting in 1800 or in 1900, it's a different amount of years. We also have some country level studies by Jan, who actually starts in 1820 with real data. So that's really nice to see. And in terms of scenarios, we don't have like fixed plans. So in some of Jan's papers, we even extended to 2100 to look at kind of circular economy, stock saturation ideas. In other work, we have only looked at 2050. So I think it's a bit of a change depending on kind of what we want to look at. But I think the long-term dynamic is the real interesting thing to see.
Thank you very much, Dominic and Jan. With that said, we'll move to the fourth presentation. Next speaker will be Nico Heren from NTNU Trondheim and ETH Zurich. He's an adjunct professor at the Industrial Ecology for Industrial Ecology at the Norwegian University for Science and Technology, NTNU in Trondheim. He's also a lecturer for prospective environmental assessment at ETH Zurich and a sustainability specialist at the City of Zurich. His talk will be about towards open community data for global bottom-up modeling. Nico, the floor is yours.
Thank you very much, Christoph. Yeah, hello. Thank you very much for having this opportunity. This is really a great session. It's really exciting to see these interesting contributions. This may be a bit of a shift of gears. You won't see a single result slide here. I'm really focusing on the work we've been doing in the past and reflecting a little bit on that and where I think what can help us for community modeling. And I try to change the perspective a little bit. So I hope you weren't expecting any results from our UN project or something. So everything I will be showing here is certainly a very strong collaborative effort. You will see a lot of names dropping up. In the end, we have a lot of references. Stefan played a key role in many of these things. Especially we mentioned Odm a couple of times already, or the UN project, which I will be talking about. So this is certainly a strong collaboration. So the background and also the overview of this talk will be, I will be talking about this United Nations Environmental Programme International Resource Panel report that we recently, or last year, published last year on resource efficiency. I will be looking at the tool chain we used there, the models we used, and elaborating a little bit on the background that, that never gets placed to publish anywhere in a paper. It's more the soft factors, how we dealt with data and how we, struggled with the model tool chain and so on. Then also I would like to focus on two publications that either contributed data or looked at data contributions in general, how to realize that. And finally, I would also reflect a little bit on my role as an editor for data, as a data editor in the Journal of Industrial Ecology and the Scientific Data Journal. So REC, sorry for the acronym, Resource Efficiency and Climate Change. So that is the UN report that I just mentioned. We looked at basically at the resource efficiency potentials from today until 2060 or 2050, and the potentials for cars and buildings. This is a bottom-up archetype MFA model. It is a very strong collaborative effort. It was kicked off by Edgar Hertwig at Yale Center for Industrial Ecology. And we had different teams intersecting with that. So it is, like you can see the tool chain. We have different parts of this model. It's an entirely open tool chain. All of these parts can be basically reproduced, can be downloaded, and it is more or less possible to reproduce all the results. So that means the input data, the code, and also the output data are basically all open access. So let me please elaborate here a little bit. So first of all, we have this is like a very simplified version of how the model works. We have on the one hand, we collected the stock data. Then we have to forecast, we have to do like a future extension of this data. So this was the part where Thomas Fishman was mostly involved and leading the effort. Then we have a sector model, which was looking at the resource efficiency or material and energy efficiency of cars, which informed then the stock model, and the same for the sector, for the building sector. We had a dedicated sector model, which was developed by myself. And those are informing the stock model. So Odm, that is something I don't need to explain here anymore. That is really the backbone of the whole thing. And then in the end, we have the impact layer. So I would like to go through the individual steps a little bit more and reflect a little bit on the data challenges and the collaborative challenges that we encountered. So at the very beginning, the data collection part was actually a huge effort. And something, you would never publish anywhere, like how hard it is and what you had to do. We had a bunch of people helping us here. We had a lot of students, PhD students contributing to that. I think in overall, there were at least 10, 20 people contributing. We also directly contacted experts and authors of publications, which sometimes proved to be the most successful way to get this data. But coordinating all this collaboration in data collection was really difficult, and we realized very quickly we need to have good tools and guidelines to facilitate that. So we needed to tell the students what we are looking for, what kind of data, who is doing what, to have an overview who's doing that. And also the technical barrier, that was something that, you can't give every student an Odm lecture for 2 weeks when they just do like a part-time help assistancy in your chair. And then we developed a couple of tools for that. So we created data collection guidelines where very specifically, specified the data quality that we are looking for. It has to be in a certain format. We had an overview of what kind of data we are looking for. So we first of all, of course, needed stock data. We needed material intensity data. We need energy intensity data and so on. We created a data repository of ourselves, very low tech. It was basically a Dropbox folder where everybody could contribute. We created a certain hierarchy in this Dropbox folder. So for instance, there would be RB for residential building, under subfolder USA for the US, H meaning historical buildings, and so on, energy intensity, and the person contributing the data. So it was like a really low technical, low effort way to contribute your own data. Then the students had a certain Excel template where they would fill the data, had a cover sheet where they had to specify exactly how to reproduce the data, where to get it, and also exactly what the units of this data are. And then also we had a data management structure. So the students were mostly people collecting data, then there were reviewers. So these were the people that were familiar with the model. So they could help the students if there was any question, if this data is useful or not. And finally, there was the database managers. That was mostly Stefan and myself partly, that made sure that the data was actually integrated in the main Odm database in the end. Then going into the individual parts of the modeling tool chain. So first of all, the Odm model, yes. It is mostly Stefan's brainchild. That is pretty clear here, I think. The idea was really, on the one hand, it facilitated our whole project, but it was also the idea to have this community model, MFA community model. And I think the previous example showed very well that this has caught up speed. It is an entirely open source model, as you all know, and we also created our own adaptation. So the Rec Odm model was the backbone of the project, and it has also been released in the specific configuration that we needed to run our model. And then there's the scenario forecasting. So that is the work by Thomas Fishman and many others of our group. So we also needed to extend the SSP future storylines that the EASA put out. So it has mostly GDP and population and so on. But we were lacking like simple factors like, square meter per capita or a number of cars per person, all this kind of stuff. So we, Tomer led this effort to come up with this expert consensus approach. And we created these target tables and scripts to interpolate the stock to the future target values. And also Tomer came up with a fancy regression model for floor area for a couple of countries. So this was also an entirely open process, and the models as well as the data are available openly. And then we have the REC model, the sector models. On the one hand, there's the transport model. So Esther has been mentioning before, we want to connect different models, and that is what we realized here. We basically created scripts that allow us to run simulation models. So in the case of the cars, we had the NREL FastSim model, which is a model that calculates energy demand. And then we were playing around with the material intensity of the cars. And then we could recalculate the new energy intensity, as weight obviously has a strong influence on energy consumption of a car. So this was like also an open calculation routine, which has been published by Paul Wolfram. Then the building sector model is very similar. We have archetype models, so different model buildings are included there. In the background, it runs Energy Plus, a sophisticated energy simulation software. And again, the software framework and the data have been made open, completely open. So that concludes a little bit the work we've done on the UN report, at least the tool chain, but there were also a few spin-offs. Let me put it that way. I think the material intensity database, that is something that Tomer Fishman and I published 2 years ago. It was certainly inspired by the UN work. We collected basically a lot of data points with material intensity in buildings. And the thing that I would highlight here is it's not only a data contribution. So this work has been actually, I was surprised, it has been cited a couple of times now, and a lot of authors are using the data. A lot of people are promising to offer data. So if you have data, please feel free to contribute it. But it was also really meant as a community database. So we came up with clear guidelines, how to contribute to data, how does the data need to be encoded? What is the data quality that has to be existent? What is a null value, right? If you know, if there's there's no wood reported in a building, do you put a 0? Do you put no value? What do you do? This is all like in a very precise way codified in a code book. So this comes with this GitHub repository here. And the goal was really to give people guidelines how to create new data sets or to extend the whole database. So the goal was really to have a living database, a seed for a growing database. And then something else, Stefan could explain much better than myself, of course, that is the Industrial Ecology Data Commons. Maybe you have come across this. It's openly available on the website of the University of Freiburg and in Stefan's group. So there you can, by now, I don't know how many million data sets you can download. It is really impressive work, again, led by Stefan. And there we also we put a lot of effort in how to encode data. How can we make data useful, like especially in the context of industrial ecology? So we found a method to differentiate the data into 7 different types, data types. So we found flow, stock, object properties, process parameters, and so on, where a good way where you could represent basically all of the data. And the nice thing, again, I think we will be talking a lot about harmonization later on. The nice thing, again, is now you can download this data directly from the website of the University of Freiburg in an Excel format, and you have a unified format, and you can do meta-analysis on top. You can integrate it directly into your models and so on. Finally, some of my experience in the Journal for Industrial Ecology. There we created mandatory data guidelines, but also optional data badges. And in the future, you will also be able to do data contributions in the Journal of Industrial Ecology. I think this incentive really works. A lot of people are actually contributing the data, and once they do, they often also contribute the code with it, which is really a surprise to me, but they probably figure, yeah, I might as well. Or they can also easily be encouraged to do so, which is really great, I think. So sometimes I dropped the authors an email and said like, hey, why I can't make sense of this data? Can you help me somehow? And they were like, yeah, let's publish the code as well. But on the other hand, everybody uses their own formats again. So everybody, we have a lot of silos. Everybody uses the Excel file that was just convenient for them. I think there's still work to do. The JIE was really pioneering this. Now a lot of publishers such as Elsevier are also pushing for open guidelines now. So taking a step back again, I think it's pretty clear to all of us here in this panel, I guess, open models and open data facilitate industrial ecology research, but there's still a lot to do in terms of how we connect, how we can make this meaningful. Data contributions are becoming a first-class citizen in journals, which is, I think, very cool. So now you can also publish your data, which is well accepted. I saw that with our publication in Scientific Data. It's being, cited a lot and being used a lot. And I think the actual benefit of this, like the material intensity database, is the data harmonization. Often with harmonization, you unlock data to people. There's a lot of silos and everybody publishes their stuff. But only with harmonization you can enable people to really use the data in a broader sense. And naturally, some data is simply unusable without the code or without any documentation, and vice versa. Code and data are also often useless without the documentation. So some points we might be discussing also now is representative data is still scarce. So again, looking more at the MFA and building sector, maybe. We don't have good data for good archetypes, especially in developing countries. Material intensity is still a bit elusive. We need those to have benchmarks for material flow analysis. For MFA and LCA, the discussion between Esther and Dominic just earlier showed that a little bit. There is still a lot of silo work going on, and I think harmonizing these processes could really help. And then, as I said before, in the developing countries, we have still very little data present currently. Okay, that concludes my talk. The word is back to you, Christoph.
Thank you very much, Nico, for the very nice presentation as well. Round of applause once again. And in that case, I would like to open the floor for quick questions towards the presentation directly before we then go into the panel discussion. Anyone who would like to address a question directly to Nico? Right, that doesn't seem to be the case at this point. In that case, let me ask you one question. Would you say that we need some, because you said that the harmonization is quite important. Would you say we need something like concordance tables, which are quite common in input-output analysis, specifically for MFA studies, or is that something we can directly use from input-output tables and stuff?
Mm-hmm. Is concordance tables something like translation tables, mapping processes onto one another? Yeah. Okay, thank you. Yes and no, but you would still have the problem that, you know, sometimes a certain data set is, I know it for buildings, sometimes there's different types of floor area, right? There's the energy reference area, there's the gross floor area, there's the net floor area, and they can differ quite a lot actually. And you wouldn't, you know, that will still remain unresolved, I think, this issue. So I think it needs a bit more. I think we need really guidelines on how to document stuff and how to, yeah, what floor area to use, for instance, all these kind of things. So I think a little bit more effort is required too.
Thank you very much. All right, is there any other direct question? Dominic, or?
Yes, maybe. Thank you, Nico, for the great presentation and also for all your efforts actually in doing all of this for the community. I would be very interested in your reflections as being a data editor. How well is this really being picked up? And do you think people, let's put it the other way around. I feel this tension between giving out your data for real and still having to hold back because of competition, because of pressure to publish instead of, you know, handing out things, fear of being scooped for all kinds of things. I mean, that all happens. And the more you give out, the higher the risk also involved, especially for, let's say, non-tenured researchers. So maybe you have some reflections on how this goes on behind the scenes, and if you have something to offer here on this point.
And this is, of course, a very good question. That is why the data badge is optional. So only people willing to share the data get to share the data. I'm honestly, personally, when we started with that, I didn't expect to see many data contributions, but it's much more than I anticipated. So I don't know. It's I guess the people that don't want to share the data, they, you know, if there's a badge or not, they will still not be, you know, they will still not do it. Maybe looking back at my own career, you know, as a you know, ambitious young PhD student, I also was like a bit secretive maybe about my data and not sharing that. But now I really realize it's usually missed opportunities. It's like you know, you also make your work more attractive simply, you know, because people, once they see the data, they find it useful, they will read the whole paper, and, you know, and they will cite it. And I think people should rather see the incentive. And I think it also drives for collaboration. People will reach out to one another and ask for collaboration. And yeah, I would encourage everybody to share the data, of course. But that's when you ask me, of course.
Yeah, I think there's a difference here between universities and say consultancies. Consultancies have to fight for their place in the market, while universities are funded with public money, and usually it's even mandatory. If you develop something with public funding, that you actually make it available to the public. So, but for consultancies, this is of course different, and we've noticed that tension as well. I'm curious, Nico. You say quite a lot of people have contributed to the database. What may help is the way that they are acknowledged. So I'm not aware of how you do that. Could you enlighten us?
I think almost everybody who contributed like one bit of data has been at least named in the acknowledgements. So, I mean, in the case of the UN report, it was simple. It has a large acknowledgement section, but also some of the people that contributed more data and helped us, you know, process the data and all, they were also even became co-authors. As simple as that.
Okay, well, that's great. After that, or has the input of data stopped after this publication?
Is it just me, or I missed the last bit?
I was asking that you had a publication about of the data, and there's a bunch of co-authors. Has the process of adding data to the database stopped since then, or is it still going on?
It was fit for our purpose, so we did this report. We have a paper in review that does the global resource efficiency view. So for that we collected a little bit more data, but it's an ongoing process fit to our needs. But we now have more like of a base database that we can easily extend. I think this like basic effort that we had in the beginning, that is something we resolved now.
Thank you very much, Nico. With that said, I would like to hand over to Stefan now for the bigger panel discussion. So we're opening the floor once again, getting together all 4 presentations that we had, and Stefan will now moderate the panel discussion. Thanks a lot for that.
Yes, thank you, Christoph, and all the speakers, all the participants. First of all, the credit for this session goes to Christoph. So he pushed this forward. He said we have to have this. He managed all the things, and you see the turnover here is really great in the contributions. So this is a really valuable service to our community, Christoph. Thank you so much for that. Quick observation from my side: we see that our research has entered a new age. It's becoming more interdisciplinary. This we see clearly from the presentations, right? We add energy emissions layer, we add demand. It's becoming more collaborative already. It's becoming more interlinked. This is what Esther mentioned, right? That we have to make sure that our models can link to these big integrated assessment models and others that do a lot of stuff already, but are maybe not so good on the material layer. We have this competition versus collaboration tension that we already discussed. Our system is getting more complex because we have this interdisciplinarity, right? We need to manage more data. And also this links to a challenge that we have a lot of detailed data on one side, but maybe more accurate data on one side. So how do we make sure that, for example, all the data that G has on the cement in energy intensity actually are used also by other models? So we have challenges on how we can actually cumulatively work together. I want to stop here. This is all great. The plan for our session that Christoph and I checked during the chat is we will now have one question to the panel, and then we will open to the panel of the presenters, and then we will open to everybody on another question. And the question to the panel or presenters now is in the chat: what are your current actions towards transparency, reproducibility and comparability, so the theme of our sessions. What do you already undertake or plan to undertake soon to make sure that the research becomes more professional along those lines mentioned here? Who wants to start?
Well, maybe I just start. Yeah. Very good question. So, I mean, I think the obvious one is something that Esther already mentioned. Most of our funding is forcing us to publish open access. So this is kind of a standard for us, also for many years. Since before it was mandatory, I think open access is really important, and also to some extent to provide data files, provide a proper supplementary information at least. I think for us right now, at least for me in my mind, I think the challenge is to take this to a more systematic level, these kinds of full open data, open access publications, because if you have a 100-page supplementary information, this might be useful in some cases, but in many cases it will be more of a graveyard than a useful resource. So I think getting to a level where you find a kind of a workflow which has an acceptable amount of additional work attached to it, but still gives you a good documentation and a good summary and a good way for other people to reuse your work. I think this is really challenging. And this is something I would say that we are currently trying to figure out how to get there, because we always have funding constraints and time constraints, and prioritizing usually leads to the situation that we already have. That's from my side.
Maybe I can add to that. The work that Sebastian is doing for them at the global level related to image that is also made available. I think both the data and the Python program actually. So that is in his GitHub. You can all access that. The national level work so far, we did publish the data, the underlying data, but not yet the model. This is something that still needs to happen. And indeed, as Dominic also says, yeah, it takes time, it takes effort, and yeah, when is a good moment to actually do that? It should be done, I agree, but yeah, everything that can be made easier to actually do that, like a repository that is really helpful and relevant, that would be a good thing.
Yeah, maybe I can briefly jump in. I mean, so as Stefan says, like we have more and more people publishing their stuff, their code, their repositories and all. But I even see that becoming almost an issue now. Like, you know, I think we need, especially in a community like the industrial ecology community, we still have maybe the capacity, we are small enough to agree on certain guidelines maybe. So I want to go back naturally to my point of harmonization. So, you know, I could imagine that there is a data quality guidelines for MFA, you know, so a document that is agreed by everybody in this community, and that kind of says like, okay, if you talk about the flow, you mean that, you know, that's really like kind of the standardization. And also this goes a bit back to what Dominic said earlier. Like, I think I almost posed the counter question also, like, how do we get peoples out of their silos? Like academia has this pressure for innovation. Everybody wants to do cool stuff and publish cool stuff. But sometimes it takes some extra effort to dump it down, to make it simpler, to document it well, and then, you know, harmonize the data so that it adheres to a certain standard. So I wonder really where could be an incentive, how we can create new incentives for that.
Thanks, Nico. Esther, did you still want to say something because you were unfortunately interrupted again?
Okay. Yeah. Oh, sorry. Go ahead.
Then Gilles, please.
Oh yeah, so I also like to add on a little bit on this transparency, especially also the comparability, because I think, for example, I can only speak for the cement and concrete cycle. I'm only working on these, but I do know there are many MFA researchers working on other materials, and the difficulty for me is when you are working in different segments, you tend to use the terminologies used by each segment. And when you want to harmonize all the material cycles in one central space, then it will take a great effort to harmonize like terminologies and the way how you deal with the data. I'm just wondering if it is possible to have an initiative like which brings together researchers on different materials, and then for example something like cost action, so we can talk about what kind of terminologies we can use, and we make this kind of effort, this harmonization effort like permanent, and then we can build on this joint efforts.
Exactly. This is another highly relevant thing, right? The common systems understanding and the terminology that builds on it. And I think, Dominic, you want to straight respond to that?
Well, only if nobody else wants to go. I just wanted to mention that there has been 20 years of efforts to harmonize economy-wide MFA. And the key unlocking part was that people managed to convince statistical officers to actually do that work. Because we as researchers, I mean, how should we compile huge amounts of data and maintain all of that? That's just not feasible in my opinion. So I think that the real question is, how do we get the issue on such a high kind of urgency level that this is being developed? I mean, we see it for energy. Look at International Energy Agency. We see it for a lot of other issues where huge amounts of impressive data are being assembled. For materials, we don't have that yet at that level. So I think that would be more productive than us trying to pull that off, I think.
Yeah. Well, that's actually a very good point, I think. It's also something that we discuss a lot in the framework of the circular economy for the Dutch government. Central Bureau of Statistics, they have a lot of data, really a lot. But it's all flow oriented, not stock oriented. So, and this is something I think that they should engage in also to collect data on stocks, not just on flows, because it's an essential part of the whole economic system. And they're open to that. Of course, it's new work, and they don't have the money for that, so then there need to be additional funding that goes their way, etc., etc. But it is something that can be discussed fruitfully. And then via the national offices, it can go to EU level. And then, at the international level, there's the UN statistics, where already the material flow database, material flow count database is established now. That can be expanded. So I think this is a very valid point. We are not the ones that should keep up and maintain those databases. It's government-related institutes like the statistical offices that have to do that.
I also like to follow up on Dominic and Esther's comments on how to have a dialogue with governments, and but I also like to point out that so the International Energy Agency has developed a lot of data on energy, and actually our work is contributing a lot to the global climate change mitigation. And actually, I think IEA is also developing something, along material efficiency, MFA. So I'm just wondering if it is possible to have a dialogue with them, so we can also borrow some of their insights, or maybe we can integrate our effort with their initiatives.
Sure, I can quickly report on that. I was part of such a dialogue, and it's it's not a direct collaboration because they have their own business model, right? That links directly to the collaboration versus competition we had before. It's different cycles. So usually it's a one-way exchange. They ask us for data. They will probably also approach you at some point for data and insights. And then we process their results. So they have scenarios for decarbonization and so on that we use, and again, as a starting point for our model. It's not a proper scientific collaboration, but there's definitely mutual exchange and updating. Nico, you wanted to say something? And Nico, before you start, I will after that open the floor to everybody on this question. If you are making any efforts on transparency, reproducibility, and comparability, you will have a chance to report this to us. That will be really highly interesting and relevant. Nico, please.
Thank you. Yeah, I'm just teasing a bit like Dominic and maybe also Esteban. Is it really not our job? Maybe, you know, we as like the most informed on material flow and stocks, and I think I can even, you know, as Christoph mentioned in the beginning, I'm even a representative for the city of Zurich, and in my experience in the one year I've been working there now, I think we like to be informed by research and academia. I think we have a certain responsibility as researchers to also share our and you know, give insights and propose things. And I mean, yeah, I think we have the best insight, and we should also come up with proposals. Really.
I think, of course, we should do that, especially in a new area like the whole dynamic material flow accounting. There we have a big responsibility to make them aware of it, to do some first studies with it, to show what it can do, to establish a first database. But when it becomes routine, and in the circular economy policy of the Netherlands, that is actually the idea, that it will be, those stock accounts will be made periodically. Then it becomes routine, and then someone else, like the statistical offices, have to take that over. So in the beginning of such a field, yeah, obviously, then academia has a big role to play. We have to sort of point the way. And then the established institutes take over in the end, and then we do new things.
Thanks, Esther, everybody. Quickly before we jump over, I think Edgar, you're raising your hand because Nico, you were calling also for guidelines. Actually, we have such guidelines already. They were released just 2 weeks ago. You know, there is the board of the material flow analysis or socioeconomic metabolism section, and we say, hey, for transparency, for proper system and indicator definition, we now have a set of guideline documents. I highly recommend everybody interested in checking out this document. It's on the parts we are talking about, not very elaborated. It's a basis, right? But it's definitely something that is already there. Edgar, please.
Yeah, I think it's sort of important not to crack. And of course, if I'm a research entrepreneur, I'm not going to wait for statistical offices to start collecting data, right? There are so many ways in which we can get data now. And, you know, the community is already employing using satellite data, remote sensing, commercial databases, software from different engineering fields and databases. So there are so many ways in which we can collect data that waiting for the statistical offices, I think, is a very slow prospect. But of course, in the end, we can hope for that this will come. But there I have the concern that it will be mostly based on national solutions. And so the Netherlands is probably early out developing like that, as they have been with other environmental statistics. And the danger is that we get lots of ad hoc solutions that are created to perform particular policy questions that are currently on the topic. And what I see with economic statistics is that we're still struggling with differences in the different systems of national accounts that have been created. And the UN is then trying to harmonize, and there are sorts of various rationales for why countries stick with the particular solutions they have found. which are normally not very good arguments, but they concern like having to revise past statistics and not knowing how to do that. And so I think that if the community comes up with some guidelines, that would probably form the kernel of this development. So I think it would be a very good idea.
Just to be clear, that is not at all what I suggested, that we should wait until statistical offices have collected data. Not at all. In the end, they have to go there. That is what I was saying. And of course, yeah, the hassle between statistical offices to align their data is terrible, but it does happen. Within the EU, the Eurostat has a function like that, but also outside it, United Nations has. So yeah, it's a very long process. Only part of it, I think, is the concern of academics.
Thank you, Edgar. And we can not only provide guidelines, we can also provide tools for them, right? Web interfaces to databases and so on, data reconciliation software, many of which was already talked about here. So officially, we are at the end of the program time-wise. Of course, we will stay here. If you want to stay here, we will continue the discussion, but feel free to follow up on your other obligation. It was a great discussion so far. After that, we have the Wonder breakout room and the poster session. So please check the IE Day program for this content too. It's highly likely that some of us will also migrate over there. I still would have to figure out how that exactly works to continue some discussion, maybe even make some concrete plans. For those of you who want to stay with us now, the floor is open on this question, and I have also the question of what is your efforts on data transparency, reproducibility, and I put on another question on the vision. Just let me put this into the chat. If you say, hey, where would you, if you reconvene in 5 years, where would you see us? What should we have to achieve by then? Dominic was so kind to put in the Wonder meeting room for us to continue then, but for the like until 7 p.m. it's over here sharp, or whatever your time is, but the next 17 minutes we will stay here in this meeting. So please, we are excited to hear about your insights, your experiences, and your visions on this important aspect of dynamic MFA research. And it's best if you raise your hand with this yellow hand, and it's easy for us to see.
Yeah, Stein, go ahead.
Yeah, I kind of have a question about the, because when we talk about statistical offices, they often come up with these beautiful numbers like national totals and global totals and different categories and so on. And then sometimes when you start working with it, it adds up nicely and you realize that they must have done an MFA in order to produce that data. Sometimes it does not add up nicely and you realize that they collected it from disparate sources and it just presented like that. And almost always it's impossible to find out where the numbers come from exactly because I think partly because of confidentiality, they can't show all the individual data points and they don't tell you how they fill data gaps using, for example, income data like GDP and so on. And so if we want data to be really like transparent and useful, I guess also from the statistical offices, we should have a complete description of how they got to their numbers to avoid mainly the risk of us sort of like taking the numbers and then breaking them down again in odd ways that are not consistent with how the data was produced in the first place. And, you know, just to avoid basically problems of large inconsistencies in how numbers are first created and then used. So yeah, I'd be interested to hear any comments on that.
Who would like to comment directly?
I guess someone who has worked with statistical offices for longer than us needs to answer here, but I really want to support your question here because I have never seen an uncertainty estimate for GDP, but we all know that it can't be an exact number that's just not feasible. But you will never get it, because at least the reason that I was always told is that statistical offices don't work with uncertainty. There is no uncertainty to their data, because that's the truth. What they are doing is the truth. That's the reported truth. As Edgar mentioned, revising past data is very, very tough, because then you say your past work was not correct. But maybe someone else has better comments than me.
Yeah, there's no uncertainty. There's only inconsistencies. But yeah, very similar impressions from my side. So with the data, I haven't worked directly with a statistical office, but the data that I've used all of the time, I'm questioning, because I'm working particularly on the metal sectors, and then you have material flows or trade commodities, for example, that are called like tungsten and articles thereof. Yeah, okay, what does that even mean? Does that include all kinds of chemicals? So what is actually the tungsten share in that material flow, and so on? So if I really want to use that trade data, it's a whole mess, and very often the documentation is really problematic, and therefore, yeah, what Esther said, like waiting for them to fill that documentation gaps, probably going to be well, then I'm going to be retired. I'm only in my early career, so still, I think working together with them and telling them what exactly we need, I'm totally fine for them for that. Waiting for that, problem, very problematic.
In the course of developing these MFA guidelines, we open up an interesting, potentially useful channel to Eurostat, where people are quite interested. The main conflict here is that we as MFA research first start with a graphical system definition, right? We have the processes, exactly the flows, everything is very clear. They don't think in such terms. They think in data cube models. So just, have lists of specifiers and then the numbers. They think more in tables. And there was the MinFuture project, a EU project that started trying to change this, right, to bridge these two worlds. Our standard may be different, but I think it's not only about, hey, we need data and this is how you should do it. There's really also a difference in thinking, that we say, of course, what you do is correct, but it can be even more helpful if you also think in terms of graphical system definitions, because then it's obvious where the mass balance is, and it's obvious that it's paper waste and not plastic waste that is included here. And these things, which one of my standard exercises in teaching is people have to use a statistical report that has tables over tables and put it into graphical system definition. It's a nightmare. And they should do the job for us, right? They would say, hey, we have tables, it's all balanced. And by the way, this is also how it's all arranged. So it's clear what goes where and how to define recycling metrics and so on. So there's still also education that needs to be done. We need to educate us better about these underlying procedures, how the data are obtained, what their inconsistencies / uncertainties / gaps are, and what value is already there. I think sometimes also we don't appreciate this well enough, the actual work that goes into these statistics. And on the other side, I think they need to appreciate more that the data can be made more user-friendly and also can be made more explicit in terms of what they mean.
If I may raise a question, probably to Nico and Stefan, going a little bit from data back to the modeling and back to Odm, how do we get to Odm version 1.1? It's like, because you started that, you put out the model, it's on GitHub, it's a community project, obviously, but I don't think the version really officially has changed since then, and it's now 1.5 years ago. But Dominic and Jan have been working on that. I have been working on that. The whole CML Leiden has been working directly with Odm. And all of them, I guess, have made modifications in one way or another. So which kind of how do we, as a community here in ISE, decide which kind of modifications become a part of Odm? And what can you comment on that, Nico and Stefan?
Stefan, you want to go first, or should I?
I can try. I have to be honest. I'm very enthusiastic about community modeling, but I'm also a beginner here. I'm still learning the different. We have organized this Odm on the GitHub repository, and there's standard workflows, right? The easiest way is you do a pull request. You say, hey, I developed my own Odm version, I want this to, I think it should be part of the next main version. So I submit such a pull request, and then I could review and say, hey, this blows up everything else. No other models will work anymore. Or we say, hey, this is a useful addition. We can do that. So this would be a more iterative, step-by-step evolvement, right? And then this Odm could branch into something that's adopted to Monte Carlo simulations, something that is conducted more to having maybe more optimization integration. So this would be the bazaar paradigm, right? So different people's, first of all, please let us know about your changes to the model. That's the most important thing, right? Basic then via such pull requests. And then we could decide how we organize the branching in emails, also discussing a dialogue. Hey, should this be a completely new version? Should this more, no, this is an alternative version. That's something we have to be has to be discussed, and I'm very happy for Christoph that you asked this question. The other alternative software design is the cathedral, right? We sit down in a workshop and say this should be the next Odm, and we should integrate it with those people and those people. That is also possible. Honestly speaking, at the moment I'm at capacity. I haven't planned that yet, but that could change in the near future. Also here in Freiburg, we will be able to hire a programmer for a few years and so on. So there will be additional resources we can chip in. So my final thing to say here, the bazaar part, so everybody please report your extensions, your bugs that you find, and we will figure out how to structure these new versions. And I could take care of this cathedral part. I promise next year. I think that is realistic to see what, you know, what we have learned so far, what could be a next iteration on something that's even more helpful and accessible.
Yeah, maybe you can briefly elaborate. I think industrial ecology or science in general has been inspired very strongly by computer science recently, and like as exactly as Stefan says, like the whole GitHub and Git thing, it's very powerful, but we still all, including myself, we struggle to understand it really. Like these tools like forking branches, these allow exactly that. Like as Stefan says, like the bazaar thing should be the 1.1 version. The cathedral thing should be the 2.0 version for sure. But if you like, I really need to point back at all of you guys. I mean, if you have something cool that you did now in Odm Meso, and you think like the Monte Carlo thing, that should be part of Odm, please make a pull request or create a branch that, you know, at least it's out there and others can pull it and try it out, you know. I think this is, yeah, we need to continue this thinking, and also computer science, what they often do is they have very extensively used mailing lists. So maybe that's something we can use our forum for, or maybe use the GitHub issues for that. I don't know. But I think that there also needs to come up the discussion, like what would I like to see in a 1.1? What would I like to see in a 2.0?
I have a quick question regarding, you know, so for beginner, so I'm actually regarding Odm, I'm a beginner. I'm also trying to, you know, to integrate my data into Odm, but I'm a little bit struggling with, you know, where I should, you know, start from, and I think, or maybe I'm just wondering if it is possible to have some tutorial like with visuals. We know like something like a video posted on YouTube, so everybody can have access to the tutorial. So we don't have to read, you know, the documents and to go through all the codes, and we can have some step-by-step, you know, tutorial, and which allows the beginners to, you know, to speed up the process.
Yeah, thank you. There is in the Industrial Ecology Open Online course a section on it. I'll put the link in the chat. It's could be better, but there is a start, different stages getting more difficult and complex. So I'll share this with you in a moment, and the link that Nico has, yeah, on YouTube.
Okay, thank you.
All right, I think with that said, maybe it's time, Stefan, to thank once again our panelists, because we're approaching now the next session. So I guess we can close this session here. Thanks, Stefan, for moderating the panel discussion parts also, and for co-hosting this session together with me. Thanks, Dominic, Nico, and Zhu, who are still here. Jan is also here, just hasn't activated his camera. Thanks again for all your very nice and interesting presentations and the really good discussion.
And of course, for doing all this community development, contributing here, being open source, signing up for the gold standard at the Journal of Industrial Ecology. I mean, I think we benefit a lot from each other. Like on the modeling, right? We learn from each other's mistakes. We build up on each other's software, on our data. And our research is gaining relevance due to that. Thank you for that.
So let's keep Nico busy as the data editor. All right. Thanks, everyone. I will stop the recording now.